Here's the TA demonstration, group 1 metals reacting with water. Here I have 3 600 ml beakers that I've filled about halfway full with water. I'm going to add some phenolphthalein indicator to each. Next, I have already pre-taken samples of each metal. I'm going to need to cover each with a wire mesh. As you can see, the pieces of metal are all sitting on the surface of water while they are reacting. As such, you can tell they are lighter than water. Looking between all 3 beakers, it seems our lithium is the least reactive, sodium is the second most reactive, and our potassium was the most reactive since it reacted completely almost instantly. As you can see, there was flame on the potassium and sodium, showing that there is a lot of heat being produced during these reactions. As you can see, our phenolphthalein indicator in each of the beakers has turned its pinkish purple, showing that it is now a basic solution in each of our beakers. I am now moving on to my second solution, lithium chloride, dipping into my solution, placing into the fire. You can see lithium is burning a scarlet or crimson red. Next, we are using potassium chloride. You can see our potassium is burning a violet color in the flame. Our last solution is sodium chloride. As you can see, the sodium burns a bright orange or yellow. And that is all for our flame test. Here for periodic trends, we have our reaction of group 2 metals. So we have a magnesium beaker and a calcium beaker. I'm going to take a piece of pre-cut metal for each, and I'm going to add it to a small bit of water in the beaker, which contains acid-base indicator. So I've now added my DI water, so I will add just a couple drops of phenolphthalein indicator. And now I can take and add my sample. First notice that you can see our calcium has sunk to the bottom of our beaker, and our magnesium has stayed floating on the surface. So you can see that calcium is heavier than water while our magnesium strip is not. We will now wait 10 minutes observing how each of these reactions goes. Here we have 2 test tubes that we have set up for our reaction of calcium and hydrochloric acid and magnesium with hydrochloric acid. I have my pieces in my weigh boats. Now I can take and measure out my 3 molar hydrochloric acid. I need 5 milliliters in each. Now I will take each piece of metal, first my calcium, and then magnesium. As you can observe between the two, our calcium is reacting quite vigorously, almost instantly, reacting completely with the hydrochloric acid. The magnesium is taking slightly longer to react. You can see that there was gas being produced as the reaction happened, and you can see heat as there is still steam forming. Both tubes have now fully reacted. You can see there's no trace of either of our metals remaining. Our calcium reacted incredibly vigorous, going and reacting almost fully with the hydrochloric acid in a short moment. Our magnesium took longer to totally react and dissolve, and you can see that heat was produced from each test tube. Primarily, more heat was being produced in our magnesium, as evidenced by the water droplets that are now forming on the top of the test tube from the steam that was going and escaping. Here we are going to continue our investigation into alkali earth metals, or group 2. Here we are testing for solubility. We have our well plate lid with our labels to tell what chemicals we are using where. To start, I will add calcium nitrate. I only need to add 1 to 2 drops per well. I'm going to start up here in the upper left. I will be adding my magnesium nitrate. After that, I will be adding my strontium nitrate. And then lastly, barium nitrate. As you can see, all of our solutions here in our well plate are clear. So next up, I will begin adding our other side, starting with sulfuric acid. Next, I will be adding my potassium oxalate and acetic acid. We again only need 1 drop. Lastly, I'll be adding sodium carbonate. Our calcium nitrate did not react with our sulfuric acid, neither did the magnesium nitrate. However, our strontium and barium nitrate both reacted with our sulfuric acid. Only our magnesium did not react with our potassium oxalate, and then our strontium, barium, and calcium again also reacted with sodium carbonate, but our magnesium did not. So our magnesium has not reacted with anything. Our strontium has reacted with all 3, as has our barium. And then our calcium nitrate has only reacted with our potassium oxalate and sodium carbonate. We can tell that our strontium and barium are much less soluble than our calcium and magnesium. So as you descend, if you're on a column, our solubility decreases, since our strontium and barium reacted in every single well. However, our calcium and magnesium, we are not able to make as much of a conclusion due to the fact that our calcium is no longer soluble in potassium oxalate or sodium carbonate. Our sodium carbonate, it is partially soluble based on how it is not fully clouded like the potassium oxalate. However, our magnesium nitrate is showing that it is soluble in sulfuric acid, potassium oxalate, and partially soluble in sodium carbonate, which brings us to question whether or not our magnesium nitrate solution is good, or whether it was made improperly or has gotten old, since we should expect to see some form of precipitate in our sodium carbonate well. So we can make our definitive conclusion that strontium and barium are less soluble than calcium and magnesium, but we need to bring into question our magnesium solution in order to fully tell the trend between calcium and magnesium. We are moving on to periodic trends, our combination of halogens and halides. Here I have my well plate lid. I have labeled my halides and my halogens. I'm going to start by putting my halogens in my well plate lid. First off is my chlorine water. only want 1 to 2 drops in each of my well plate lid. If you can see, our chlorine water has a greenish yellow tint to the solution. Next, I'm going to be using my bromine water. As you can see with our bromine, it has a yellow or brown tint to it. Lastly, we have our iodine water. And our iodine solution is a deep brown or deep red. To each of these, I am now going to add my halide solution. For chlorine, I will start with sodium chloride. Next, I will do my sodium chloride to bromine, and then iodine. Next, I will use sodium bromide. All of my halide solutions are colorless themselves, they're clear. You can already see in our column of chlorine water, it has reacted with our sodium bromide. It has changed from clear to a green-yellow tint. Lastly, I will add my sodium iodide. As you can see here, I put my chlorine water 1 well up from before, so just note that that is my sodium iodide well. And now, as you see, in both our chlorine water and bromine water channels, we have changed from clear and a yellowish solution to a dark brown yellow and a brownish yellow mix, showing that our sodium iodide has reacted with our chlorine water and our bromine water, and our sodium bromide has reacted with our chlorine water. There was no reaction in our sodium chloride to chlorine water, sodium bromide with bromine water, sodium chloride to bromine water, and there has been no reaction for any of our iodine water column. Now that we've seen evidence of a reaction, we are going to go back and add hexanes in order to definitively show if we do or do not have a reaction. So I have taken and labeled 3 tubes with the combinations we believe had a reaction from our well plate lid. So I'll be taking chlorine water into these 2 tubes and bromine water into this tube, and I will mix this one with sodium bromide and these 2 with sodium iodide. I have my chlorine water. Again, it's a yellowish color in the bottle. So I'm adding half a milliliter of my halogen water, which in this case is 10 drops. All reagents are provided with droppers, so this is very easy to be able to count out what we need. Here's my sodium bromide. My bromine water. It is stored in an amber bottle, so it is hard to see the color through there, but as you can see in my dropper, it is an orange or brown color. Again, we need half a milliliter, so 10 drops. Next, I will be adding my halide solution, so I will need sodium bromide for this one. All of my halide solutions are clear, and we need to add 0.75 milliliters, which is 15 drops. As you can already see evident, again, our yellow solution that we had has turned into a orange or brown tint. Next, I will be adding my sodium iodide. Again, this one is stored in an amber bottle, but my solution is clear, as you can see in my dropper. If we go and look back to our iodine, you can see that the colors are actually very similar. And as you can see now, both of our tubes that are mixed with iodine actually have approximately the same color to them, even though this solution started out as an orange color from our bromine water. This one was a very faint yellow. They are now both a dark brown. So to both of these, I will be adding hexane. I only need to add a half a milliliter to each, so 10 drops. Here's our bromine and sodium iodide solution. After one inversion, you can already see our bottom layer is becoming much fainter and we are getting a deep purple forming in our organic layer of hexanes. Now after several inversions, you can see still we have our bromine water light brown or orange color down here, but we now have a very deep purple or violet color, showing that we actually have iodine up here in our organic layer. I'll repeat the same with this solution. As you can see, we have our deep brown from our combination, and again, a violet is forming in our organic layer. Invert several times, and now we have a lighter brown as our bottom layer, and we have a deep purple as our top layer. Again, showing that we have iodine in our organic layer. Lastly, our chlorine and sodium bromide. You can see our light yellow and an orange forming in our organic layer. Mix. Now we are back to a very light yellow and a very deep orange or red up top. So this is where our bromine has formed in our organic layer. So as you can see, we have evidence now that we have formed a new halogen since they each more readily dissolve in our organic layer. We have our violet from our iodine in our two test tubes that reacted with sodium iodide. And we have an orange for our sodium bromide. So as we can see, each of our combinations has reacted and formed a new halogen in the organic layer of our tubes. For periodic trends, here is how you can observe the noble gases. You will be provided with aluminum, handheld spectroscopes, and gas tubes containing the noble gases. You will then take the gas tubes and plug them in to a power supply provided in one of the hoods. You will then turn on the power supply to see a color emit from one of the tubes. If the power supply is not functioning, you will see that no color is in there, and please get help from your TA in order to have the power supply replaced. The tubes can be hot if left on for a long time, so there will be hot hand protectors provided in order to allow replacing of the tubes. In order to use your handheld spectroscope, you will have your power supply in your hood that I have over here. You need to stand about a meter away, crouch down, and peer through the spectroscope until you can find the light. When you have it, you should start to see the diffraction on the side of the spectroscope, and you will be able to see the wavelength of light. So as stated before, your spectroscope, stand about a meter away, get a head-on view of the lamp, and look.